Basically, now we've got 3 presentations that are going to talk about aspects of teaching sustainability. Leah from Birmingham, Alison from Wrexham Glendower, and Chris from the University of Surrey. Won't waffle on anymore. I'll hand straight over to Leah.
Wonderful. Thank you very much. So I'm sure that some of the topics that I'll cover today, everyone is very familiar with. However, what I want to do is kind of whiz through some slides that I would use to start off activities with students. I find that I hope everybody else does as well, to find that students are not just concerned with understanding the technical aspects of exploring and operating in space, but also with the ethics of doing so, and with the future and how we'll be able to continue to use space with the vastly increased number of launches we have, particularly into LEO. So one activity that I like to run has to do with the launch site locations. I start off with the sort of the context of space launches in general, which are that humanity doesn't really have a brilliant track record of taking care of near Earth space. So I use one example that's quite old, Project Westford, which not a lot of people have heard of, particularly younger students, which is an attempt in the 1960s to facilitate global radio communications, in which 480 million copper dipole antennas were placed into MEO, and they were meant to provide passive support to Westford's parabolic dish. The first launch produced only clumps, which was not very useful, and the second launch was better, but it was still only between 25 and 45% is the estimate actually dispersed properly. Some of them are still in orbit today. This figure is actually quite an old one from the NASA Orbital Debris Quarterly News in 2013, but it shows that there are still clumps of these needles in orbit, and obviously it's quite a lot later than the 1960s now. So I kind of start off with that example, and then also talk about where launch sites are. So there's this diagrams of orbital launch site locations in the little blue bubbles, like the ones you get on Google Maps. Lots of them are near the ocean. So for instance, Cape Canaveral and Kourou, but some are not. So the ones in red, Baikonur and Jiuquan. And so I show this slide and I ask students to consider what the impacts are of having launch sites in these locations. Not only the environmental impact and the nearby location of human populations, but the ease of debris recovery from launches, and also any military interest that people might have in having launch sites in these locations, because they can double as missile launch platforms. So one thing that I like to do with students again is get them to consider where specific launch sites are. So Baikonur and Plesetsk are used by Roscosmos. They are not on Russian soil. Access to the sites is very restricted and they are quite remote. So I had the students do a literature search on on studies of these launch site locations and debris from the launch site locations, and see what they come up with. And generally they'll find a bunch of Elsevier articles of varying quality when they do this literature search. And then we'll go through what's in the data and consider some aspects of the studies themselves, as well as the data that's within them. So generally what we find when we do this particular version of this particular activity is that the studies of the environmental impacts of launches were all written by about the same group of authors. It's a relatively small group of researchers who do this work. They're all funded by the same funding body. The articles that are published tend to lack some crucial evidence. So, for instance, exact sample site locations that would make it possible to repeat and verify the studies. And they all conclude there's no environment impact by the launches that take place at the sites. So, after finding this out, usually I ask the students to put together a little position summary on what they think about the ethics of the research. Is there a potential for bias? Has it been mitigated well? If it's not, what would they need to do to independently verify these conclusions? Can it be done easily? And do we need more studies on debris retrieval and environmental impact for sites, say, by the oceans? And I also asked them to consider who has funded the research and what their interests might be in the conclusions. I realize there's a fair amount to unpick there, and there is also an emphasis on the way that we conduct research and the ethics of doing that, as well as so it can be quite a general discussion, not just about launch sites, but there's a lot to kind of a lot of directions you could possibly go in with this kind of activity. Okay, so here's another idea for an activity that you could run with students, and obviously this is very topical given that there is such an increase in launch traffic into LEO. And so I've taken these images from the ESA Space Debris Report, which comes out annually. This is the one from 2021. So I do need to update these slides. But it shows, I mean, the most dramatic bit of this, and this is obviously not going to change with the addition of another year of data, is how much launch traffic has increased and in the last few years, and how much of it is commercial rather than defense or civil. Again, this shows the dramatic shift in mission type. So this shows that a lot of the satellites that have been launched recently are communication satellites. And finally, this one shows the pure dominance of the Falcon launcher, which is absolutely phenomenal, coming from pretty much nothing 10 years ago to being almost the entirety of the market now. And until someone else develops a reusable launch vehicle, this is likely to continue. I like to contrast this, the increase in the launch traffic in LEO to that in GEO, and this shows it pretty starkly that there hasn't been much of a change. If anything, there's a little decrease in launch into GEO, and the distribution of interests between civil, defense, and commercial has stayed. The balance between those has stayed pretty much the same. The same goes for the types of missions. And the launcher types, again, you can see that the Falcon is creeping in there, but it's not nearly as dominant as it is in LEO. So after I scan through this data, I then show them this plot from Bryce-Tech. So Bryce-Tech issues various reports. The most recent launch review that they've published is from 2020. And so this shows sort of the distribution of launch types in a different way, and then the number of spacecraft. It shows the number of spacecraft being launched has increased a great deal, and this is related to the size of the spacecraft that are being launched, which are much smaller commercial satellites into LEO. And so if you have students review the data from the ESA Debris report and from that Bryce-Tech report, you can run a nice little activity in which you have students kind of try to analyze the data a bit, try to work out what the differences are in the launch traffic, what can we project that might happen in the future from this, and try to understand kind of how the landscape of space is changing, and what sort of clarifications, what further information we might like to have that is not necessarily contained within this data. So this one's about this activity is about getting students to ask critical questions about what we know about launch, about this launch data. And then the final one that I wanted to talk about was a debate. So I like this activity a lot, and the students really enjoy this one. If you decide to run something like this, I would suggest setting aside at least 3 hours in a tutorial for it, because it takes some time to do. What we do is we set up a debate between SpaceX and the astronomers. So we start with Starlink, because most of them have heard of it. And this visualization from Leo Labs shows the current positions of the Starlink spacecraft around the Earth. And there are, and I have to keep updating this slide, by the way, there are 2,400, over 2,400 and over already. Not all of them are operational, but they are all there. and the most recent launch was about 2 weeks ago. So it really has not been, they really are just continuously going up. So in response to concerns about this massive constellation, the SpaceX did lower the original planned Starlink orbit from 1,200 kilometers, and they also tried out an anti-reflective coating for called on what are called dark sats in response to scientists' concerns about it. So then, introducing the perspective of the astronomers, this is a dramatic image, but it's from the telescopes, the Chilean telescopes at Cerro Tololo Inter-American Observatory. And what it shows, those streaks are the 19 Starlink satellites passing from the field of view of their observing camera, rendering about 1/5 of it unusable. So this is from late November 2019, and as I say, it's quite a dramatic image. It got a fair amount of press. However, this is obviously not going to be an isolated incident, because launches are planned for every 2 weeks, continuing through the next few years. So to run this debate, it actually requires some preparation by the students. And I've put up here, I know this is not easy to read, but but I think we're going to provide the slides afterwards, so you can mine this as you will, and obviously add things to it as well. So I put a bunch of resources up on our virtual learning environment to help the students create their arguments. So there's some popular press that articles that I put up there, and I update that fairly regularly. And then there's some conference presentations and some scholarly articles on the impacts of the Starlink satellites, mostly the impacts of the Starlink satellites on observations made by astronomers. So I asked the students to use these to help themselves in constructing their arguments, and they break up into teams and look at, separate out the articles and look at them during the tutorial. So it requires them to work at some speed. Then we structure the debate. I've explained to them how it's going to work, and one team will be SpaceX and one team is the astronomers, and they have to work together to come up with a compelling argument for the launch of additional Starlinks, or against the launch of additional Starlinks without any further visibility mitigation or any further restrictions on how many or where it'll go. So they have to nominate a speaker or two speakers to present their arguments. They then present their arguments. They have 10 minutes to come up with a rebuttal, and then a different person from each team has to present the rebuttal. And then the teaching staff judges them while everyone else waits. And I have found the several times that I've run this, that the students are extremely engaged with this activity. They do a good job of at least scanning the articles that they're given. This is particularly important for their understanding of how to parse a scientific article, and it goes nicely after the launch site activity, if they've done that one, because that also requires them to read scientific articles. And so they are very passionate on both sides of the argument, and generally this, even though this is quite a long activity, they are never bored. So I like to follow this activity up as well, and you can use this if you want to as either a formative or a summative form of assessment. So I always run this poll to ask about students what their opinions were beforehand, what they thought about it beforehand, and then what they thought about it after, and what factors most influenced their opinions. And they are very much swayed by a good argument. Is what I've found from this. Whoever it is that does the best job of constructing their argument, whichever side of it they are on, that is the side that pretty much all of the students end up on. And so then it's worth following up on this, because it helps to tell the students that, you can have the best technical argument in the world, you can, have a deep understanding of how constellations work and how orbital mechanics works, but if you can't make a convincing argument for something, you probably won't sway the public or politicians or anyone who might pay for your work. So or not pay for your work, as it were. So it's a really, I find it a really sort of powerful teaching tool. And as I say, the importance of following up after the debate is can't be overstated, to kind of give the students a feel for how they've done, and for how they need this more holistic view of how to use space, rather than simply understanding a load of equations. They do need that, don't get me wrong, but the understanding the context around it, I feel, is also extremely important if we're going to produce a bunch of space engineers who have an appreciation for maintaining sustainable space. So those are my 3 examples. There are lots of other things, other ideas and ways to approach this, sustainability in space, and I've just put a little list here of other questions, other aspects that you might want to consider or use to form the core of an activity. So one would be, for instance, okay, the astronomers have this problem with making observations from the ground. Why don't we just move all their observatories to space? As has been suggested by someone whose name I shall not say. Then there's the consideration of the rights to the land, say where launch sites are based. Is it okay for countries to operate launch sites on soil that belongs to someone else? What are the impacts on their communities? What are the impacts in particular on Indigenous communities? And this is obviously one that the astronomers should be very familiar with, because their telescopes are often sited on native land, and there are a lot of debates going on over whether or not those sites should be expanded or not, and how they should operate in future. There's also the consideration of dark and quiet skies. And once again, this ties back into the rights of Indigenous peoples. And then there's, as Dr. Mamatha was speaking about, there's the risk of debris risks and the adequacy of mitigations for casualty risk, as well as for in-space collisions. So there are lots of directions you could go with this. And I hope that, that you might take some of this on board. Yes, that's me done, I think. Thank you very much.